Hello, everyone. Welcome to the last talk of the day. My name is Shiyu Zhou. I'm a postdoc from Perimeter Institute. First, I would like to thank the organizers for organizing this conference. And this short talk, I'm going to tell you my recent work on universal quantum phase classification on quantum computers from machine learning. And at the end, I'm going to briefly preview my ongoing work on using agentic AI to discover quantum phases. So quantum phase classification has been a long-standing problem in condensed matter physics. The more traditional way is to use the order parameter based on symmetry, but it fails to capture the more exotic topologically ordered states. Then people came up with topological entanglement entropy. However, it is also known that there exists topologically trivial states that exhibit non-zero topological entanglement entropy. And in this work, we aim to develop a universal quantum phase classifier based on the machine learning models. And it takes the data, specifically the shadow data from quantum computers, and is model independent in the sense that it does not rely on any kind of Hamiltonians. So our method relies on the equivalence of quantum phases based on the finite depth local unitary, in the sense that two states belong to the same phase if they can be connected through a finite depth local unitary evolution. And our goal is to identify the phase of a given quantum state by probing only the information on local patch of size L. So to generate data, we consider a reference state psi belong to a certain quantum phase, and we evolve it with finite depth local unitary circuit, with each local unitary being Haar random. And at the end, we have this state psi prime. And notice that the psi and psi prime belong to the same phase by definition. And then we perform the random measurement at the end on the local patch of size L. And we record down the random angles, the angles of the random measurement along with the measurement results. And in total, we obtain ns number of shadow data of such angles and measurement results. Notice that this kind of data can also be acquired from quantum computers, but for this project, we are simulating them through using DMRG. So we repeat this process multiple times for different random unitary circuits and obtain this final data set of the dimension MB, NS, L, and 4. The MB stands for the different random unitary circuits we're considering. So notice that this kind of data set does not require any knowledge on the Hamiltonians and neither the knowledge on their ground states either. Furthermore, this kind of randomly evolved states naturally explores the full breadth of the quantum phase and generates very rich data set that does not depend on any specific basis or any specific order parameters.
What is N sub S?
Oh, N sub S is the number of shadow samples you take. Yeah, NB is the number of random unitary circuits you consider. L is the local size, and 4 is the number of. This is the architecture of our machine learning model. It consists of 4 parts, and I'm going to discuss each one in detail. The shadow reconstructor basically maps the 4-dimensional raw shadow data into a higher dimension, enabling richer interpretation for the later components. And the mean pooling basically takes the average over the shadow samples and outputs a 3-dimensional tensor. And then it's a time series machine learning model. It is basically the heavy lifting part of our model. And then in this work, we consider 3 different kinds of time series machine learning models, which are the bidirectional recurrent neural net, and transformer encoder, and 1-dimensional convolutional neural net. Surprisingly, we find out that all of those 3 gives us relatively similar results. So I'm only going to present one of them. What this time series model does is basically captures the long-range correlations among spins at different sites and outputs a matrix that is independent of the local patch size L. And finally, we have this final reconstructor, which is another feed-forward neural net that produced the probability of predicting the phases. So to demonstrate our model, we consider these two following states, the product state and the GHC states. Notice that these two states cannot be connected to each other through a local unitary, finite depth local unitary circuit, hence they belong to two separate phases. And in a physical context, you can think of these two states as the ground states of Ising Hamiltonian at two extreme limit of two phases, the trivial phase and spontaneously symmetry breaking phase. And to generate data, we involve these two states with depth 1 random local unitary circuit, and at the end, measure a patch of size L equals to 6, 8, 10, and 12, and acquire the shadow data. And our shadow samples we consider is 10,000, and the number of random unitary circuits we consider is 2,000 for this specific case. And once we have the data, we concatenate them together to feed into the model. And once we train the model, we evaluate our model on the data set with 2,000 trivial states and 2,000 spontaneous symmetry breaking states. And the classification accuracy is shown on this heat map for different NS and L. And we see that the accuracy reaches pretty high, 0.96, when the sample size is 5,000 for patch size L equals to 12. And furthermore, we observe that at relatively low sample size, 200, the model can already give out reasonably good accuracy around 0.8. And to further demonstrate the effectiveness of our model, we analyze our model on the two Hamiltonians, the Ising model and the axiom next nearest neighbor Ising model. Notice that although the ground states of these two Hamiltonians are not in the training data set, our machine learning based model can actually reproduce the phase diagram. So for the Ising model, we see that our model is able to reproduce the sharp phase transition. However, the transition point is being shifted. And for the axial next nearest neighbor Ising model, there are 4 different phases: the ferromagnetic, the antiphase, and the floating phase, and the paramagnetic phase. Notice that the ferromagnetic phase and the antiphase actually corresponds to the same Z2 spontaneously symmetry breaking states, as they can be connected to each other through a finite depth local unitary circuit by simply flipping the space. And then we can see that the machine learning model actually can classify the ground states of any model very well, and was able to reproduce the phase diagram. And notice that we have a floating phase here. This floating phase is basically a gapless phase with long-range correlations, and the indecisiveness of our model in this region indicates the signature of the floating gapless phase. I would also like to mention that our model is quite efficient compared to some of the full tomography-based measures. For example, the newly developed geometric entanglement measures. We can see that our machine learning-based model can achieve relatively good accuracy at a lower cost of the sample size. In the future, we would like to extend and test our model in a higher dimension, specifically topological order states. And we would like to see how robust is our model against the noise, and finally test on the real quantum devices. And then I'm going to switch gears to talk about my ongoing project that I'm very excited about, is to use the agentic AI to discover quantum phases rather than just classifying it. So for the recent years, we've seen many fields have been using agentic AI for scientific discoveries like chemistry, biology, material science. And for this work, we try to use the agentic AI to discover quantum phases and hopefully can discover new quantum phases with the framework. So the task we give to the agent is the following. Given a Hamiltonian H with tunable parameters, theta, which can be lattice geometry or coupling strength, and an initial starting point theta 0 at phase A. And we ask the agent to explore the parameter space automatically to discover other phases. So this is the task that we're giving to the agentic AI. So here is how it's going to work. We have an agent, and this agent is given access to an environment, which is a differentiable Hamiltonian solver, which can be exact diagonalization or DMRG. And the agent is going to perform the following actions. First, it's going to query a set of quantum states around theta 0, the initial Hamiltonian parameter, from the environment. And it learns a latent representation Z using autoencoder on this set of states. An autoencoder is basically a neural network that can learn to compress the data to a lower dimension. And then the agent, based on what the agent learns, will optimize the Hamiltonian parameter based on this rule that the agent needs to move toward to states that with latent representation deviating from the latent representation. And specifically, the loss function takes the form as the absolute difference absolute value of the difference between the learned representation and the new representation with a minus sign to maximize the distance. I slept a lot of details under the rug, so if you're curious, we can talk after the talk. So pictorially, this is what you can imagine. You can imagine a Hamiltonian parameter space, and then there's this baby agent. And the baby agent initially sits at phase A at a single point, and the baby agent starts to probe the environment around her. And then, after she learns something about the environment around her, she tries to move away toward to some other space in this parameter space. And then with repeating this step over and over, hopefully the baby agent can move to jump to different phases. So this is the way you can think about this framework. And notice that all of these are automatic. There's no supervisions. The model just does it itself. Since it's an ongoing work, I'm only going to show some preliminary results. And this is some preliminary results on the agent learning, landing at different phases for the known models. So the first model we are using is the Ising model. The agent first starts at the ferromagnetic phase and over time was able to jump to the paramagnetic phase. And then the other model we are using is the XXZ plus transverse field model. And notice that instead of just single parameter, here we have two parameters, delta and H. Initially, the agent is at the ferromagnetic phase, and with 10,000 steps, the agent was able to land at the anti-ferromagnetic phase. So with that, I would like to thank my awesome collaborators and thank you for all of the attention. Thanks.
In the agentic AI for phase discovery task, are you separately learning the autoencoder representations and training the autoencoder?
Yes.
Okay. So
that's part of the
that
framework.
First, and then you're trying to maximize the distance.
Yes. So in principle, this learning latent representation is performed on every single step when you try to move away, but we can reduce that. There are a lot of details we can talk about it, but yes, to answer your question, yes, we have to train the autoencoder along the learning path.
I see. Okay.
Any other questions? If not, let's thank the speaker again and thank all of you.